ready to rock and roll. We're having this presentation about iOS 6 security by Dowd and Tarjei Mandt. Dowd was a founder of Asmuth Security. He worked for years as a senior researcher at IBM ISS X-Force and as a principal security architect at McAfee. Tarjei Mandt works as a senior vulnerability researcher at Asmuth Security, and he presented at Black Hat, Hackers to Hackers, and Hackito Hackathon. Welcome.
Okay, so my name is Dowd, and this is Tarjei Mandt. We're here to talk about iOS 6 kernel security. We decided to look at the iOS 6 kernel because we'd heard that there was a lot of mitigations coming in, and we wanted to see like what strategies they'd employed and how they compared to other operating systems and stuff that we've looked at before. So this presentation is basically the result of that research, and we're going to basically run through like the mitigations that iOS 6 has introduced, and also we're going to specifically focus on the security improvements regarding mitigation of kernel exploits, which are a critical part of most jailbreaks. We noticed that a lot of the strategies that they employed were targeting things that have been used in jailbreaks before or spoken publicly about before. So we wanted to provide an overview of the new kernel-based mitigations that there are, and also we'll discuss a few techniques that we came up with for attacking the iOS 6 kernel, and at the very end we will show a demo of installing CDR on an iOS 6 device and running essentially jailbroken. So we've got two major parts of this talk. The first part, we're going to talk about defense, where specifically we're going to mention the heap hardening strategies that have been introduced in iOS 6. We're going to mention stack cookies, various information leaking mitigations that have been implemented, the address space layout randomization that has been added to the kernel, and also some user kernel address space hardening. And then part two, we're going to talk about some offensive techniques, including some information leaking strategies to bypass some of the ASLR mitigations put in place in iOS 6. And we'll also talk about a few primitives that we developed when developing exploits for the iOS 6 kernel that you can mix and match, and they should be useful for building exploits that will work against iOS 6. So I'm going to pass over to Tarjei to start talking about the heap hardening.
All right, so we're going to begin to talk a bit about the randomization algorithm, because this is what all the mitigations use for generating stack cookies, heap cookies, the kernel map ASLR, and obfuscating pointers, which previously could be used to learn locations in kernel memory for objects. So this algorithm gets a seed generated by the bootloader, iBoot, and it combines the C with the current time to get the random value. So as you can see in this slide, we have this function which takes these parameters and shuffles them around in order to produce a 32-bit random value. And the seed itself it's based on some interrupt times. So the heap hardening part is really what tries to address past attacks regarding zone allocations and attacks on free lists. And there are basically three mitigations put into place. We have mitigations involving pointer validation, block poisoning, and free list integrity verification. And this is, as mentioned, specific to the zone allocator, so it concerns all the functions like zalloc, kalloc, malloc, malloc zone, iomalloc, et cetera, et cetera. And before we go into this, I just want to recap a bit on the old exploitation techniques, or recap a little bit on the zone allocator. So the zone allocator allocates memory from these zones, which are fixed size, which hold fixed size chunks. So you have like kalloc 8 bytes, or kalloc 16 bytes, or 3,268 bytes. And there's also specialized zones for specific tasks. So you have like the PMAP zone or the VMAP copy zone, et cetera, et cetera. And when you allocate memory, these zones allocate pages on demand. So they're not contiguous in that sense. You can have a calloc 8-byte zone located next to a calloc 16-byte zone, et cetera. So yeah, like I said, you allocate blocks of pages on demand. These pages are divided into same-sized blocks. And when you allocate a page in order to use as a zone, you divide this block and put all the blocks in a free list. And this is a single linked list. So the first pointer in each chunk holds the pointer to the next entry, et cetera, et cetera. And when you allocate something, you simply just take the first element on the list and serve it back to the user or the component that requested the allocation. So this is an example of the calloc 8 zone where you have the free list and some chunks are used and some are not. So the previous exploitation techniques in this space involved overwriting these pointers. Since they're singly linked, there's really no checking. You could just overwrite the pointer and have it return any memory really. And the way this was leveraged in an exploit was that you would typically have it point to the syscall table, then use that to overwrite a syscall entry. And subsequently, by invoking that syscall, you would be able to divert execution to an arbitrary location. So in iOS 6, they attempt to address this in multiple ways. One is to prevent, one of the goals is to prevent invalid pointers from being entered into the zone free lists. And this is done by performing additional checks on the pointers before they are entered into the list itself. So in this case, any pointer that is put in is verified to be in kernel memory, so OX 80000 up until this upper bound. If the allow foreign variable for this specific zone is set, no additional verification is performed. But if it is set, it also, or if it's not set, it's also checked if it's within the zone map defined for that specific zone. We also have block poisoning, and this is a mitigation introduced to prevent use after free style attacks. So whenever something is freed, the strategy here is to fill the blocks with sentinel values. So in this case, it's dead beef, in order to prevent you from reusing values like use after free or tainting these values. So in this case, it's only performed on selected blocks, and this is because of performance. So if the block size is smaller than the cache line size of the processor, it will automatically fill the chunk with dead beef. If it's larger, it won't use this mitigation unless you have specific parameters set. The third one is more on preventing exploitation altogether by trying to address the overriding also of the free list pointers. So when you boot up the kernel, two random values are generated by a function called zone bootstrap. One is a 32-bit cookie for poison blocks, and the other one is a 31-bit cookie for non-poison blocks. And these are used as validation cookies of the next pointers themselves. So so the free list pointers at the top of the free block is now validated against these cookies. So this is the heap cookie version introduced in iOS 6. Actually, the verification, in order to verify, they do not change the top pointer, but they store an additional pointer at the end of the chunk that is the encoded version. So in this case, the non-poison cookie is used if you're not using dead beef, if you're not poisoning the chunk. and the poison cookie is used if the chunk is small enough to be fit into the cache line size of the processor. So this is, to validate this, they ensure that they try both cookies. So if the poison cookie matches, they also check, if all these values are dead beef. If any of those values are not dead beef, it will cause a panic. If the other cookie matches, the cookie is checked, and yeah, that's it. It's also worth noting that when you allocate something, the next pointer, these cookies are actually zeroed out, or they're replaced with dead beef in order to prevent you from actually leaking any of these values. Another thing concerning the hardening of the zone allocator is regarding primitives. So Stefan Esser had a talk at SciScan and Black Hat called iOS kernel heap Armageddon, where he proposed a technique using OS unserialized XML to basically manipulate the state of the calloc zone. And this allowed you to precisely allocate and free calloc zone data. And it was also possible to force persistent allocations by creating enough references. So you could basically, if you created enough references, you could freeze the reference count. So when this, say, dictionary was no longer used, you would still have these objects in memory. And this was useful in order to, cause persistent allocations and so, things like that. So this was an example he came up with, where you had all these references, and that would, produce an OS object that was never freed in memory. In iOS 6, they addressed this by making sure that if you have duplicate dictionary keys, they no longer, free the original key, which was one of the exploitation or scenarios he came up with, because if you would be able to free original keys, you could create holes and position the memory in that state you wanted. And the dictionary entries can also no longer be pinned to memory using these multiple references. They're both checks on this now. And in both of these cases, the plist dictionary is considered invalid. So this technique is pretty much, it's mostly dead now. So that was on heap. The stack cookies are also used, and this is, obviously to prevent the stack overflow exploitation. It's applied to functions with structures and buffers. The random value that is used to see this cookie is generated by the kernel on boot as well in ARM inits. And although it's a 32-bit value, there's only the entropy is only a 24-bit, because the second byte is actually zeroed out. And this is presumably to prevent you from using a string copy operation to guess the cookie or bypass this in some way. And they do this by both having a generated stack cookie placed directly after the save registers on the stack, at the bottom of the stack. And they also store a pointer to that cookie or to a location in the kernel data section and compare those values. So this is what that basically looks like. You see that the stack cookie pointer points to the kernel data section, and the verification is then to compare that value against the cookie value that is stored on the stack. Yeah, so this is also showing that this is before a function returns in the function epilogue. It verifies the stack cookie by dereferencing the stack cookie pointer and comparing that to the stack value. And if this check fails, it would obviously result in a kernel panic. So Mark's going to continue to talk a bit about information leaking mitigations.
Okay, so previous versions of iOS, as you probably know, didn't use ASLR. So basically, they had quite a few. They have quite a few APIs that are available from user mode for disclosing various pointers to objects in kernel mode. these are usually pointers to objects on the heap, useful data structures and stuff like that. Because in the past they weren't using ASLR, this was not really a big deal. It wasn't very important. But now that they're trying to randomize all the data in kernel memory, then it makes sense to try and prevent some of these APIs from disclosing useful kernel mode addresses that might be used as either overwrite targets or as part of some exploitation strategy. So essentially what they did was they disabled a few APIs. For the bulk of APIs that disclose kernel pointers, they actually obfuscate them. And then there's a few others where they just zero out pointers where they decided they didn't need them. The first thing I wanted to talk about was the disabled APIs. Now, Stefan Esser actually talked about a method of using heap feng shui in his Black Hat 2011 talk. And one of the interesting strategies that he noted was that there was several mark APIs, specifically host zone info and mark zone info, that will actually disclose the state of the kernel zones to a certain extent. So you could query a zone and find out like how many blocks it's allocated, how many it's got free, all this kind of status about each zone. And this is particularly useful when you need to know precisely how many allocations you need to fill up a zone and stuff like that. So these APIs were particularly useful for heap grooming and stuff like that. So Apple, of course, decided that this wasn't particularly necessary for users to have, so they now require, the APIs still exist, but they now check if you've got the special PE icon has debugger access, which of course by default you don't. There's also a large bunch of APIs that disclose kernel object pointers as part of structures that they return to the kernel. A few of these are BSD system calls, but a lot of them are also mark APIs that are exposed by the kernel. And a lot of them would disclose pointers like mark port K object will expose a pointer to a kernel object. Some of the others, port space info would give pointers to port objects, page info, and so on. So like there was all these really useful pointer disclosures that you'd be able to use in mounting an attack against the kernel. So basically, Apple went through and fixed all the ones that you see up on the slide in front of you. Essentially, all of these APIs still return the same structure, and they still have the field where the pointer is, but they've actually gone ahead and obfuscated it. Basically, these APIs are also used internally to some extent by the kernel itself. So they can't get rid of them and stuff like that. And a lot of the pointers serve as unique values and things like that. So they still needed them to be unique values, etc. But they didn't want to give away the kernel pointer. So basically, they just have a simple strategy for obfuscating those pointers. And what they do is they generate a 31-bit random value at boot time, and they'll add that random value to the real pointer. So the structure you read back will have a nonsensical value. So this is an example of a structure they used to return beforehand, and you can see like this structure, which eventually gets passed back to user mode. It's filling out information about a pipe, and you can see that the pipe handle value is actually just a kernel pointer. Whereas now we've got a disassembly, as you can see, they've got the a random value that they now add to it. One thing I should mention about this particular example that I chose is in the latest XNU source code, the source code still looks like this. So Mountain Lion has actually been lagging behind iOS in a couple of these protections, and some of their APIs are still exposed. I haven't actually verified on Mountain Lion whether they're their compiled version is still vulnerable to this particular information leak. But I might do a blog or something where I enumerate the differences that Mountain Lion is still lagging behind and mention them where appropriate. But we were specifically focusing on iOS, which has fixed all this stuff. And then there's a couple of other APIs that disclose pointers unnecessarily, and so they just zero them out. In particular, there used to be a known proc structure information leak using sysctl that some other jailbreaking things used, and so they've just gone ahead and gotten rid of that altogether. So now that they've prevented the kernel from disclosing all this stuff, they want to do some address-based layout randomization. Obviously, this is designed to prevent attackers from modifying or utilizing data at known fixed locations, which was a very big problem in previous versions of iOS. So they basically have a strategy that has two parts. The first part is they randomize the kernel image base of where it gets loaded, so it's no longer at a static location in memory. And they also randomize the base of the kernel map, which is something I'll talk about more in a minute. Okay, so the kernel image is actually randomized by the bootloader before iOS is running. They generate a bunch of random data, and then they take a SHA-1 hash of that data, and they take a single byte from that SHA-1 hash, and they use that to calculate the kernel slide, which is, in effect, you can see on the slide the formula that they use to calculate the new base of where they're going to place the kernel in memory. So it's basically a constant value plus slide times 2 meg. So you can see in the disassembly there, this is actually the code in iBoot that works out where they're going to load the kernel, and it basically mirrors that algorithm that I mentioned on the previous slide. The calculated value that they work out is then added to the kernel's preferred base address. So as a result, because they're using a single byte for randomization, the kernel can now be rebased at one of 256 possible locations, and the base addresses are 2 megabytes apart. And I should mention that they only randomize the kernel if MHPy is set in the header, which of course it is on iOS. Anyway, the adjusted base address of the kernel is passed into the kernel in its boot args that iBoot passes to the start function of the kernel, so that the kernel knows where it is in memory. The kernel map is basically describes the entire layout of kernel memory. It's a special map for the kernel task, and basically every allocation that happens within the kernel is allocated from the kernel map either directly or indirectly, most usually indirectly. So basically it's used for, the kernel map spans the entire kernel address space. It starts at OX80000 and goes up to OXFFFE, FFFF. All the maps that we were discussing earlier, in particularly the zone map where kalloc zones are allocated out of, and there's also an IPC kernel map, and there's a whole bunch of others. They're actually carved out of the kernel map as well. So this zone map is like a submap of the kernel map. So in the past, what they used to do is, at boot time, they'll just go and carve out these submaps contiguously, and so they would be in locations that would be easy to figure out. Now, especially because of ASLR, because the kernel has moved from the base address of kernel memory, if they just did contiguous allocations now, the zones would always be at the very beginning of kernel memory, and they wanted to add some randomization to that. So basically, the strategy that they did was they generate a 9-bit value right after kmem init, which is used to establish the kernel map data structure, and they multiply this value by page size, which is 4K. And then this resulting value is basically used for an initial allocation out of the kernel map. So they'll get this. Random allocation that's, because it's 9 bits of entropy, there's 512 different possible allocation sizes. So because they multiply it by page size, this can be an allocation up to 2 meg. So what basically happens is they'll allocate this at the beginning of kernel memory, and then they'll go ahead and allocate all the submaps after it. So the submaps are now at randomized locations because of this initial allocation. One thing also worth noting is that that initial allocation that's at the beginning of kernel memory is silently removed the first time that a garbage collection is issued, which is a process that the kernel does periodically to prune the zones that we were talking about earlier. So the first time that a garbage collection runs, they check to see if their initial kernel K-map allocation is there, and if it is, they remove it. This behavior can actually also be overridden with the K-map off boot parameter. So this is an example of how the kernel map would typically look in your standard iOS device. You've basically got the random K-map offset allocation at the beginning. Sometime after that, you've got the kernel image. The stolen memory thing there refers to some memory that's manually taken at very early boot time. And then there's a bunch of zones that happen sometime after that. This is just an example. There's no reason why zones couldn't be before the kernel image if there's enough space in between the kernel image and the random K-map offset, depending on the random value that was generated for the kernel image when it was loaded. But generally, it'll look like this. The other thing to note there is there's 2 static pages in memory. There's the vector table at OXFFFF0000, and a shared com page, which is also available in user mode, actually, at FFFF1000. These are actually outside the kernel map, so they don't move. The other thing that they've done with iOS 6 is added some address space protection. I guess they did this to prevent null and offset to null dereference style vulnerabilities. Obviously, this has been quite a big deal in other operating systems, particularly in the last few years with the Windows kernel in particular. And you have SMEP and all those technologies looking at addressing this. But what Apple have done is basically, in the past, they had a similar address configuration to most modern operating systems, where you have a user mode task in the low half of memory of a virtual address space, and then the high part is taken by the kernel. Now, null dereferences were actually already prevented in iOS because they forced binaries to have this page 0 segment that essentially mandated that the first page is, at least the first page is not mapped into memory. And they actually enforced this, like if you tried to create a binary, even a signed binary without that page 0, it will just kill it because there was a integrity check. However, I guess they felt that wasn't enough because I guess there's potential offset to null style problems whereby, if, for example, a realloc failed and someone didn't notice, they might write to an offset in memory that's high enough that something's mapped there, in which case maybe you could do something. So now the kernel task has its own address space while it's executing. There's no user task visible. They basically transition into the kernel task's address space with the interrupt handlers or when you issue SVC or whatever. And they had to do some special operations to handle the copying to and from user and kernel mode within, so that they can see both address spaces at the same time. For anyone that's interested, they actually do that by using 2 translation table-based registers for user mode, where the first one points to the user address space and the second one points to kernel address space. And when the kernel is running, they just replace the TTRB0 with just the kernel address space, so it can't actually see user mode anymore. But the end result is user mode pages are essentially not accessible while executing in kernel mode, so you're not going to run into a situation where you accidentally access them. So this is basically how that looks. You can see a user task has both the user address space and the kernel map. Again, there's a static COM page that's actually visible to both the user and the kernel. And when the kernel's running, yeah, there's nothing in the low part of memory. So when I was looking into this, I looked back at iOS 5, and they had this pretty crazy copy in and copy out strategy where the only validation they did for user mode pointers was that the user mode pointer was below kernel memory. That is, it's in user mode. But they didn't check the length at all. And that was crazy because the pointer plus the length could be larger than 0x8000, and then they'd run the risk of inadvertently copying in or copying out of kernel memory while using a copy transition. But basically, there was a limitation to the attack, which is devices had to have greater than 512 meg RAM, because I tried mapping the top page in user mode, didn't work. I looked into it and eventually discovered that was why. But new devices such as iPad 3 and iPhone 5 that have 1 gig RAM will let you map that top page of memory in. And then basically you can do this copy in and copy out trick. So here's the code that does that. You can see that basically there's no length validation at all. They just, as long as the user mode pointer starts in user mode, then apparently that's fine. iOS 6 actually added a whole bunch of checks. They added integer overflow and signness checks, conservative maximum lengths, and making sure that everything's in user space. However, they're actually still vulnerable to the same bug, because if the copy length that is sent to copy in or copy out is less than 4K, then the pointer plus length check is just skipped for some reason, which means you can read and write to the first page of kernel memory for anything that does a copy in or copy out. So here's the code here. Again, you can see that there's a function called copy validate. That's the thing that actually does everything. But there's a check right before it where if the length is less than 0x1000, then don't worry about it. It's probably fine. Is there anything in that first page of memory? Well, as we know, initially the K-map offset, that random allocation used for the K-map randomizing is there, but that's removed after the first garbage collection. That means necessarily that first page of memory won't be in any zones, because the zones were allocated while the K-map offset allocation was still in place. So you need to find things that allocate to the kernel map directly, and there are a couple of such things. HFS does it a bunch of times, and actually kalloc does it for blocks of larger than 256K. They'll allocate directly to the kernel map. So it is indeed possible to map the first page of memory, of kernel memory in. So in order to attack a bug like this, basically I created a proof of concept that created a pipe, and I specify a buffer to either copy in or copy out of that was in the last page of user mode memory, and then we would be able to transition over that boundary and either read some data out of kernel memory, resulting in a useful information leak, or write into the first page of kernel memory, causing a panic or gaining privileges. One thing that was particularly interesting is because copy in and copy out are designed to fault all the time, if your allocation strategy fails and the memory isn't mapped like you'd hoped, the kernel is not going to panic. It'll just safely return e-fault. So you can actually try it endlessly without causing any damage. And then you can read back the kernel memory, check that the allocation error is the thing that you wanted to be there, and then perform your overwrite. So that was quite interesting. The other thing we should mention is that kernel address space is no longer read, write, execute. Kernel code can't be directly patched, which was a very popular strategy in the past, and the heap and the stack are non-executable.
All right, so we're going to talk a bit about, some attack strategies for iOS 6. As Mark mentioned, most of these protections now kill basically all the known attack vectors. The syscall table overrides, patching kernel code, attacking data structures, which you no longer can infer due to the randomized locations. So we basically need something new. So generally, when you want to have an exploit, you need to leak some information, especially if you want to bypass ASLR and stuff like that. And the corruption primitives also is what dictates the strategy. So do we write into an adjacent buffer? Do we write to relative location from the buffer? Do we write to an arbitrary location and stuff like that? And the different primitives in this case will be, we will look at them separately. Leaking the kernel base address is really useful because it has a lot of information in its data structures. Previously, you could use this API called kext request to request information about kernel extensions. And this API was divided into two parts. You had active and passive operations. The active operations required privileged access, so root. This was because it did stuff like load, unload, start, stop, etc. It should be mentioned that iOS, which is configured with the secure kernel configuration, removes the ability to load kernel extensions. So you can only do like unload, start, stop, and stuff like that. So before iOS 6, there were no restrictions on accessing these passive operations. So you can, as you can see on this slide here, you can access these different types. You can request the address of the kernel image by calling the request predicate requesting the request predicate get kernel loaded address. And there's a few others there that allow you to request a lot of information about the kernel environment and the kernel extensions. So in iOS 6, they try to address this, but the check was somewhat, they sort of didn't get it right. So in this process, they obviously try to prevent you from getting the load address of the kernel, but in that process, they allowed all the other operations. So while you should only access passive operations, they now allow also you to access active operations and as well as all the other useful APIs regarding disclosing information about the kernel extension environment. So now we can actually use this kext request predicate loaded, which returns a dictionary on information about all the kernel extensions. You could do this in iOS 5 as well. But it's useful to us now because we have ASLR to deal with. So this returns all the loaded addresses as well as Mach-O header dumps for all the loaded modules, including the kernel. And although the load address and the segment headers in these Mach-O headers are obscured to hide the ASLR slide, the section headers are not. So we can actually get any sort of address to any section for any kernel extension, including the kernel. So we can simply just pass it a request. Like this one, we get a response, and we decode that response, and we look at the section address, which actually is the real address. So this doesn't require you to have root privileges. You can do this as a non-privileged user, and so ASLR is very easily defeated. Yeah. Mark's going to talk a bit about heap corruption.
Okay, so as we mentioned earlier, like all the strategies that iOS 6 has employed has more or less made it such that standard heap overflow tricks are no longer really going to work out. So basically, you know, you can overwrite a free list pointer, but validation will fail, and you know, there'll be a kernel panic. So we required new strategies, and really the strategies that you employ depend on the properties of the bug you're trying to exploit. So basically, this section, we're just going to mention how, you know, obviously, since the free list validation is in place and it's hard to defeat, maybe we'll target metadata instead. That's quite useful. There's various control structures that can be quite useful. Some of these attacks will require some level of heap grooming, which may or may not be difficult depending on the block size and, again, the properties of the bug that you're actually trying to exploit. I'm going to quickly present like 4 primitives that we've found to be quite useful, and then we're probably going to do a demo of our thing. So the primitives that I came up with all revolve around this VM map copy T structure. You can see it there. It's quite a simple structure. It's got a type and an offset, a size, and then a union that has like a header pointed to a VM object, or a structure that has a pointer to some data and a kalloc size. So this structure is quite useful, particularly because of various properties that it has. Basically, the kernel has this function called VM map copy in, and it's supposed to use this when it's copying in large chunks of data from one map to another. And what it does whenever it's transferring like a large block of memory, they'll use this VM map copy in structure, which basically creates one of these VM map copy T structures. Rather than copying all the data in at once, they'll usually just create a data structure saying, oh, this data from this map we need to put it in this map or something like that. They use kernel buffers when the size is quite small, when it's less than 4K, and we can actually create these really easily. Basically, if you haven't looked at mark messaging or mark ports before, it's a really large part of iOS and the XNU kernel, and we didn't really have time to go into it in this presentation. But essentially, you have these mark ports that you can create and send messages to and receive messages from. And the messages that you send can contain things called OOL descriptors, or out-of-line descriptors. And basically, they more or less indicate when you're sending a message like, oh, I want to send all this data over here, but instead of copying it all into your message, you just provide a pointer to it, and they'll use this VM map copy in to copy it into the kernel, and then when the receiving mark port receives the message, then it will they'll copy it back out to the target process. So basically, you can just create a mark port to receive messages, send a bunch of messages to them with these OOL descriptors in them, and it will end up creating these VM map copy T structures with kernel buffers in them. And it turns out corrupting these structures is quite useful. The other good thing about them is, apart from the header, there is completely user-controlled data under it, and anything under 4096, you can basically create that size. So you can target overflows that take place in a whole bunch of different kalloc zones, depending on the bug that you're trying to exploit. So the first primitive we can do with this is an adjacent disclosure. Basically, we just you essentially groom the heap such that you've got an OOL descriptor right after your buffer that you're overflowing, and you overwrite the size parameter of the VM map copy T, and then you receive that message on the port that you sent it to, and the overwritten size will actually cause it to copy kernel memory that's adjacent in memory to your kernel buffer, so you'll be able to read a whole bunch of adjacent data. What's really useful about this attack is that size is not pass decay free or anything like that. if you're unfamiliar with iOS kernel programming, the kfree API takes a size, and that size is used to denote you know, what zone it's going to put it in out of those kalloc zones. So basically, if you put the wrong size in, you can cause some problems. But in this case, there's no side effects whatsoever. The only thing that size is used for is to determine how much data to copy out of kernel memory. So this is how they look when they're in the when they're like a data structure is allocated. You've got your user data in there. I've chosen 256, but obviously it can be anything up to 4096. It fills out the header, and you'll notice that the kdata pointer, basically when they allocate these VM-map copy T structures like this, they allocate like structure plus however much data you have. So, and then they make the pointer to the data that they're going to copy back out to user mode, like directly under the header. So as you can see, if you just overwrite the size to be much larger, they'll end up copying the adjacent memory on the heap back out to you, which is quite useful. We can take this a step further. As you saw in the previous slide, like right after the size is a pointer which points directly under it, because that's where your user data is stored. So essentially we can overwrite the size and the pointer of an adjacent VM map copy T, and we can set that pointer to anything we want, and we can read arbitrary kernel memory at this point. So we just overwrite those few members, we receive the message, and we can read arbitrary memory. Again, this is really great, particularly because there's no side effects. The data pointer in that previous slide is never passed to kfree or anything like that, so it's not going to like cause some zone corruption or something like that. And as you know, the size doesn't either. So the only thing that pointer is used for is to decide which memory to copy back into user mode. So again, this has no side effects. So using both of these primitives together is really useful because if you can perform an overflow multiple times, which you probably can, this is a very safe way to read memory back from the kernel and get the data that you need in order to perform a useful overflow. One thing I should also note is that the data pointer is never used for anything else. So we can extend this again and basically recreate an overflow in one go. So as you saw in the previous slide, or I'll show you, you can see that there's a kalloc size in the data structure right after the pointer. Now that kalloc size is actually passed to kfree, and like I mentioned before, that size is used to determine which zone that the block is going to be entered into when it's freed. So basically what we can do is we can overwrite kalloc size with a larger value than it really is, and then read some arbitrary kernel memory. The other thing I was going to mention previously is that if you're reading arbitrary kernel memory and it's unmapped, this actually won't, again, panic the kernel because it'll just safely return an error because essentially they use copy out to perform the copy, and as we talked about that before, it's not going to cause a panic, so it's quite safe. So yeah, you change the kalloc size after the data pointer and you make it something bigger, like 256 instead of 128 or whatever, and then you allocate a 256 byte block and you'll get this block back that's really only 128 bytes, and you can do the overflow again. So essentially, if you overflow one of these data structures, it allows you to do a second overflow, but in the process receiving arbitrary kernel data, which will be really useful to you in performing some sort of overwrite. So I had some pictures of this. Again, this is the normal one, and then yeah, you overwrite with a larger kalloc size, and that's what's eventually passed to kfree. The last primitive that I wanted to talk about was finding your own address and doing an overflow, which is basically a mix and match of those previous techniques. So this is basically one where we want to overflow two adjacent VM map copy T structures. And we do that in the first one that we overflow, we're going to overflow the whole thing, which involves overriding the size, the offset, the KLOC size, and everything. And this is going to be where our poisoned block is, right? But then we want to keep overflowing and go a little bit further into an adjacent VM map copy T and partially override it, basically just overriding the low byte of the pointer and changing the size to be something quite large. Then when we free the second VM map copy T structure, it'll end up leaking the page that our VM map copy T structures are on back to us. And for the uncorrupted ones and for the partially corrupted one, we will see the pointers to itself in the data that we receive back. So we'll know exactly where we are in memory. And then we can free the first VM map copy T structure, which is where the poisoned block will be, and we'll know exactly where that is in memory. So again, you've got a memory layout like this. The overflow block is presumably something that you're going to trigger your bug in. And then we basically overflow over the whole first one, which is where the poisoned KLOC block is going to be, and we partially overflow the second one, basically so we point a little bit backwards on our own page in memory, so we can read back and see exactly where we are. Using this is really useful because there's a couple of times for arbitrary write primitives that we wanted to go into, but unfortunately we ran out of time. But both the write primitives that we came up with involved basically having one level of pointer in direction, so we had to know where we were in memory. So using this trick, we were able to go ahead and figure out where we were in memory, write pointers to our own block, and then do a second level dereference and gain arbitrary execution by corrupting some kernel data structures. So do you want to set up the demo?
Yep.
So we're going to do a demo of an iOS 6 device.
Should we?
Yeah, we'll.
Yeah. So it's obvious that. Well, you want me to do the demo first? Okay.
So this is an iOS 6 device. We wanted to get an iPhone 5, but I totally failed at it. It's up a bit. So you can see, but it's iOS 6. We're going to show that we can run this app and basically install Cydia, jailbreak the phone, and do what we like. So, well, Cydia is running, but we don't have any network. So you can see that, anyway, using this strategy, we can jailbreak an iOS 6 device and run arbitrary applications, which I think you're not meant to be able to do. Yeah. So in conclusion, you can see that iOS 6 added a huge bunch of mitigations. All the previous techniques that have been used are basically, for the most part, useless. But there's still room to move, and it's still possible to exploit kernel bugs in iOS 6, but the bar has definitely been raised. So that's it. Thanks.
All right.
Oh, now it works.
Are there any questions? I see one over here.
Can you use that exploit to unlock the iPhone so you can use another SIM chip, or is that
Sorry?
kind of not unlock the iPhone?
Oh no, this is just a kernel mode exploit. It's not for
mostly
SIM
just
unlocking.
kernel stuff, huh?
Yeah.
Okay, okay, thanks.
Any other questions? Please wave your hand if you got any questions.
All right.
Nobody?
Maybe I missed this, but what bug did you use to actually overflow into the other VM copy T structures?
It's in disclosure,
Okay.
but we'll publish it when Apple is done with us.
Okay.
Last and final question.
What did you use to analyze the code flow? Just the.
Sorry?
What did you use? What methodology did you use to analyze the code flow of the kernel?
Oh, like we just used IDA, and the XNU source is available, so that was a real big help. Particularly the mountain line releases. A couple of the disassemblies we had on the slides, there's actually now source code that you can go and look at. We just didn't update the slides because we were developed that bit when the betas were still out.
Okay, I think it's time for a coffee break. Mark and Tarjei, thank you very much for this great presentation. Give him a warm applause.